It's crazy, right? Like just a little while back, these super powerful AIs were basically just reading and writing, and now they're learning to see the world and like actually make pictures. It's wild to think they're getting that much smarter.
It is. Yeah.
And that actually leads perfectly into what you were curious about. How do we give these like text-focused AIs this whole other skill set of image generation,
Hmm.
but without like messing up their language skills or needing a server farm the size of a small country to run the whole thing?
That's a great question. And it's really one of the big challenges that researchers are working on right now.
Mhm.
How do we make these LLMs, large language models, more versatile? How do we make them handle different types of data, like images, without having to completely start from scratch or basically break the bank with the computing power needed to train them?
Yeah, it seems like the obvious solutions have some pretty big downsides. The
Mhm.
research we looked at mentions the SEMV system, which just like added a whole separate module for image generation.
Right.
But that like more than doubled the number of parameters in the model, which seems kind of like strapping a jet engine onto a bicycle. Sure, you might get some serious speed, but is it really the most efficient way to do it?
Exactly. Adding these dedicated modules can definitely make the model good at the new task, in this case, generating images, but they just become so huge. And
Mm.
that makes them really expensive and difficult to actually use in the real world. It's like having a giant supercomputer in your basement. Good luck keeping the lights on.
And then the other obvious thing to try is to just train these language models on a ton of images and text together.
Right.
But that can actually make them worse at their original job of understanding and generating text. And the paper gives some concrete examples of this. In Table 1, you can see that using standard LoRi, a common fine-tuning method, actually leads to a significant drop in the model's performance on language tasks. It's almost like someone trying to become a world-class chef, but then they neglect their gardening skills and their herbs all start to die.
That's a really interesting analogy. And it's true, it might seem counterintuitive, but just throwing more data at the problem isn't always the solution. When you indiscriminately fine-tune these models, you can actually disrupt the delicate balance of weights and connections that make them so good at language in the first place. Sometimes researchers try to counteract this by adding even more text data to the mix,
Right.
but then you just end up with the same issue of needing massive amounts of computing power. So the team behind this research was trying to come up with a smarter, more targeted approach to achieve this multimodality.
And this is where I think things get really cool. Instead of just slapping on new parts, they took a closer look at the structure of these massive language models.
Yeah.
And they thought, hey, maybe there's some untapped potential here, especially within models that use this mixture of experts or MOE architecture.
Hmm.
Now, for those of us who don't spend all day thinking about AI, can you give us like a quick ELI 5 on what a MOE actually is?
Sure. So imagine you have a standard large language model, right? It's this one giant brain trying to solve all sorts of problems. Okay, now imagine breaking that giant brain down into a team of smaller, more specialized brains. These are the experts. And each expert is particularly good at handling certain types of information or solving certain aspects of a problem. Then you have this router that basically acts like a traffic cop directing the incoming information to the expert that's best suited to handle it. And what's important to remember in this research is that all the initial experts have only been trained on text data.
So it's like having a team of specialists, each with their own unique skills.
Exactly.
And the idea here is that not all of these specialists are going to be busy all the time, right? There's going to be some downtime, some unused capacity.
Mhm.
And that's where the researchers had their aha moment.
Yeah.
They realized that instead of creating a whole new set of experts just for images, they could maybe repurpose some of this existing but idle capacity within the MOE structure to learn image generation, which honestly is a pretty ingenious idea.
It really is. They basically wanted to unlock this hidden potential that was already there within the model. And to do this, they used a two-step process. The first step involved taking a standard, dense, large language model and transforming it into this MOE structure. They used the llama architecture, which is pretty well known. Yeah. And they mentioned in the paper that they followed a method of randomly dividing the neurons within the feed-forward network layers to create these expert subnetworks. So you can almost think of it as reorganizing a large company into smaller, more specialized teams.
So randomly splitting up the neurons is like taking the existing brain cells and just kind of shuffling them into different groups.
Right.
That sounds surprisingly simple.
It is. It's more about what happens next.
Okay.
So the real magic happens in how they then train these newly formed expert teams to handle images without messing up their original tech skills. And that's where their second key innovation comes in. Partial low-rank adaptation, or PLORA for short.
Plure. That definitely sounds like the secret sauce here.
Yeah.
So what exactly does it do?
Imagine you're adding these tiny little helper modules within the model's processing blocks.
Okay.
These are the adapters. And the really clever part is that these adapters are only active and learning when the model is dealing with information related to images.
Wait, so only for images, but how does the model know when it's looking at text versus an image? Like, how does it make that distinction?
Ah, that's where this idea of discrete image tokenization comes in. They use something called a vector quantized variational autoencoder, or VQVAE for short.
Catchy.
Basically, this VQVAE takes an image, which is normally represented as this continuous stream of data, and converts it into a sequence of discrete tokens. Kind of like how words in a sentence are discrete tokens.
Yeah.
The researchers used a specific tokenizer from another paper, Sun et al., from 2024, which has a vocabulary of over 16,000 different visual words. So when the model sees these image tokens, it knows to activate the Plura adapters. And because images are now represented as these distinct tokens, the Plura adapters can be specifically designed to only kick in when those image tokens are being processed.
So the model gets the stream of text tokens, and then boom, a bunch of these new image tokens show up. And the Plura adapters are like, okay, time to shine. They jump into action only when they see these visual cues. And that's the key, right? That's how they prevent the model from getting confused and messing up its language skills. And the results in Table 1 really back this up.
Exactly.
The original model, when they fine-tuned it with the standard approach, it took a noticeable hit in its ability to work with text, its original strength.
Right.
But with their Plura method, that drop was practically nothing. They were able to add image generation without taking away any of the language capabilities.
Exactly. By keeping the adaptation very targeted and focused solely on the image tokens, they avoided this problem of the model essentially forgetting what it had already learned about language. But of course, when you introduce a whole new type of token like these visual words, you can't just leave the model's vocabulary as is.
Right. You can't just start throwing around new words without giving the model an updated dictionary. So when they incorporated these image tokens, they had to expand the LLM's vocabulary to include them. They also added special tokens to indicate the beginning and end of an image sequence. These boy and oi tags.
Yes, exactly. And this vocabulary expansion requires adding new parameters to the model's embedding and head layers. But here's where they introduce another clever trick. They didn't just randomly initialize these new parameters.
Okay, I was about to ask about that because random initialization just seems kind of like, well, random and probably not the most efficient way to do things.
Right. They did something much more sophisticated. They used something called Gromov-Wasserstein distance
Yeah.
for the parameter initialization.
Now that sounds complicated. Can you break that down for us?
Sure. The basic idea is to give these new image tokens a more meaningful starting point within the model's existing knowledge. So instead of assigning random values to the new parameters, they use this mathematical technique, this Gromov-Wasserstein distance, to align them with the underlying structure and relationships of the existing text embeddings. So they're not just adding new words to the dictionary, they're giving those new words a semantically coherent place within the AI's understanding. Think of it like this. Instead of just randomly throwing new pieces into a jigsaw puzzle, they use this technique to figure out where those pieces might fit based on the existing pieces. This alignment of the text and image embeddings helps the model learn faster and more stably. And they actually show this in Figure 3 in the paper. The Gromov-Wasserstein initialization leads to a much quicker convergence of the training loss compared to using simpler initialization methods.
So it's like giving the model a head start on understanding how these two types of information, images and text, relate to each other.
Exactly.
Okay, so just to recap the main steps in their approach, they started with a text-based LLM, converted it to a MOE structure to leverage all that unused capacity, introduced these Plura adapters that are like specialists for image tokens, figured out how to represent images as discrete tokens using a VQVAE, expanded the vocabulary, and then initialized the new parameters in a smart way using the Gromov-Wasserstein distance. It's really impressive how they put all these pieces together.
It is.
So what did the training process actually look like?
So they did the training in two phases. First, a low-resolution phase where they focused on getting the text and images to align at a basic level. They used about 4 million image-text pairs at a resolution of 256 by 256 pixels and trained for 5 epochs. This got the model to understand the general correspondence between the two modalities.
Oh.
Then they moved on to a high-resolution phase where they used another 3.5 million image-text pairs, but this time at a higher resolution of 512 by 512 pixels to really improve the quality and detail of the generated images. Again, they trained for 5 epochs. They also mentioned that they used this really nice data set called Share Captioner, which has high-quality photorealistic 4-sec images and very detailed captions. And this really helped the model learn better.
It's interesting that they were able to get such good results with a relatively small data set of 7.5 million image text pairs,
It is.
especially compared to other models that are trained on data sets that are like way bigger.
Right.
The results shown in Figure 2 and Table 2 are honestly really impressive. The paper mentions that their FID scores, which is a measure of image quality, were comparable to those of latent diffusion models that were trained on much, much larger data sets. And of course, as we saw earlier, they did all of this without sacrificing the model's ability to understand and generate text.
Exactly. And they achieved all of this with much less data at a much lower computational cost, which you can see in Table 3, compared to some other state-of-the-art approaches like Mars.
Okay, now one of the things that I found super interesting was their analysis of how the MOE routing mechanism changed after they did this multimodal fine-tuning. They talk about this idea of expert redundancy. What does that mean, and what did they learn?
Yeah, so they looked at how often different experts within the MOE structure were being activated for the same input. They used a metric called expert coactivation, or ECA, to measure this.
Okay.
If you have a high degree of coactivation, it means that those experts are probably doing very similar things and that there is some redundancy in the network.
Makes sense.
Now, Figure 4 shows that the initial text train model had quite a bit of redundancy across different layers. But after they fine-tuned it for image generation, this redundancy went down significantly, especially in the earlier layers. And what this suggests is that the experts that were kind of sitting around doing nothing before were now being put to work to handle this new image generation task.
So those underutilized experts were basically being repurposed to learn about images.
Exactly. It seems like the model was able to intelligently adapt and use its internal resources more efficiently.
That's really cool.
Yeah, it is. And then they went a step further and actually looked at which experts were being selected to process text tokens versus image tokens. And in Figure 5A and the visualizations in Appendix A7, which are Figures 10 and 11, they saw this really interesting pattern emerge. They call it modality-specific and modality-agnostic experts.
Okay, modality-specific versus modality-agnostic. I'm intrigued. Break that down for me.
So in the earlier and later layers of the model, they noticed that certain experts started to specialize. They were mostly activated for either image tokens or text tokens, but rarely both. These are the modality-specific experts. But the experts in the middle layers, they were being activated pretty frequently for both types of tokens, which suggests that they were more focused on this higher-level understanding that's shared across both modalities. These are the modality-agnostic experts.
Wow, so it's like the model developed these separate processing pathways for text and images, but then it also had this shared pool of experts in the middle that were able to bridge the gap between the two.
Precisely. It's a really fascinating division of labor that emerged within the model. And it contrasts sharply with what they saw when they used standard LoRa for fine-tuning on multimodal data, which is shown in Figure 5b. In that case, there was a lot of overlap in which experts were activated for both image and text tokens. And this is probably why the text generation performance suffered. The same experts were trying to do too many different things at once, and they just couldn't handle it.
So to sum it all up, this approach is really impressive for a few key reasons. It's incredibly parameter efficient, meaning they didn't have to make the model that much bigger. And they managed to keep the original language processing abilities almost completely intact. And they achieved all of this with relatively little data and computing power, especially compared to building multimodal models from the ground up or using less targeted fine-tuning techniques.
Right.
It's like they found a way to upgrade these existing text-based AI powerhouses into multimodal machines without having to rebuild the entire engine or fill up a giant fuel tank.
Exactly. This research offers a much more sustainable and scalable path towards building truly multimodal AI systems.
So for you, our listener, the big takeaway here is this. The researchers didn't just try to force the AI to learn new tricks the brute force way.
Right.
They took a step back and realized that these massive models already have incredible potential hidden within them, and they figured out how to tap into that potential in a really clever and efficient way. And if we zoom out and think about the bigger picture, this research is really exciting because it points to a new direction for AI development. Maybe instead of constantly building bigger and bigger models and using more and more data, we can focus on being smarter about how we use the resources we already have. And if we can learn to unlock this hidden potential, this latent capacity within existing systems, think about all the possibilities that opens up.
Yeah,
Not
absolutely.
just in AI, but in all sorts of complex systems in the world around us. It's a really thought-provoking idea.
It is.
Thanks for joining us on this deep dive.